In the previous episode, we have added this instruction decoder to my homebrew 8-bit CPU. It consists of two decoder ROMs, which take the 16 instruction bits and translate them into 16 control signals that we've hooked up to various parts of the CPU. In a nutshell, the decoder ROMs implement an arbitrary Boolean function with 16 inputs and 16 outputs, which we can program to do whatever we'd like. Before we added this instruction decoder, the control signals of the CPU were wired up to the instruction bits directly. That was very convenient to get started, but it was also very wasteful and meant that we couldn't have certain useful instructions such as an add with immediate, since the ALU control bits were connected to the same instruction bits as the immediate operand. We finished last time by programming the decoder to recognize and decode the existing instruction encoding and emulate these direct connections between the instruction bits and the CPU's control signals. But since we now have this abstraction layer in between the instruction bits and the control signals, and we can program any Boolean function into these ROMs that takes the 16 instruction bits and outputs 16 decoder bits, we can go back and overhaul our instruction set architecture a bit and add a few new instructions. Let's go take a look at that. So since we now have a lot more flexibility in how we encode and decode instructions, let's try to come up with a more systematic instruction encoding, and let's see if we can add a few more instructions. Let's start with the basics. I think the NOP should still just be an all-zero instruction. And then let's think about how a move might work. Looking at how we encode instructions today, the immediate always sits in the upper 8 bits of the instruction. We also have the RS operand sitting in these 4 bits here. And then we're generally encoding the RD operand in these 4 bits here. So all the upper bits in an instruction, except for the lowest 4 bits, have some special meaning attached to them, either as an immediate or as a register address. And it's only the lowest 4 bits of an instruction that are never used as an immediate or a register address. So if we look at an immediate, which is more or less the worst case in this setup, the immediate instruction, the load immediate in this case, only has the lowest 4 bits of the instruction available to distinguish it from any other instruction in the CPU. So every instruction with an 8-bit immediate will have to have a distinct 4-bit pattern in the lowest 4 bits. As a starting point, let's say we split the available encodings in half. We'll assign immediate instructions a value of 8 or greater for these lower 4 bits, and the other instructions a value that is lower than 8. And this is just a convention to come up with this instruction encoding. We're basically free to pick anything we want. But it makes sense to have a little bit of structure in here just to make it easier to come up with the initial encoding. Conveniently, the load immediate already has an 8 in these lower 4 bits, so this will already work. And now we need a way to distinguish the NOP operation from the move operation. Theoretically, if you look at the bit pattern here, we don't use register address 0 in hardware, so there will never be a move instruction where the source and destination register addresses are set to 0. But I'm not sure I'll want to avoid using register address 0 forever. Maybe at some point in the future we'll actually want to have a total of 16 registers available, and we actually do want to make use of register address 0. So I think it would make sense to basically assume that we can have any register address placed in the source and destination operand here, including 0. Which would mean that if you wanted to do a move from R0 into R0, you would potentially end up with an encoding that looks exactly like a NOP. To get around this, let's actually keep the lowest 4 bit of the instruction as a 0, but let's use the uppermost 4 bits of the instruction as an indication that this is a move. So instead of putting a 0 here, let's actually put a 1 here. The decoder now also allows us to much more carefully indicate if an instruction reads or writes the RD operand, or whether it reads the RS operand or uses an immediate. So in case of a move, we're just writing the RD operand, but we're not reading it. I think I want to indicate this with an RD exclamation mark, and we're reading the RS operand. And similarly, the load immediate operation only writes the RD operand as well, and instead of having an RS operand, it actually has an 8-bit immediate operand. And remember that we now have the option of having a 4-bit or an 8-bit immediate operand, so it makes sense to indicate which one it is here. Let me also indicate a bit more clearly what the individual bit ranges of the instruction are set to, just to highlight what the system is that we're trying to go for. This now makes it easier to see how these instructions differ in their encoding. Let's keep going. Next up we have a few branch instructions. The jump relative with immediate already looks good. It has a 9 in the lower 4 bits, which matches with the pattern we have, that all the immediate instructions have an 8 or greater. Let me also indicate that this is reading an 8-bit immediate. And then let's think about the other two. I think it would make sense to have as many of the basic instructions use a 0 in the lowest 4 bits to indicate that this is just a basic instruction. So let's do that here. And now to distinguish these two jumps from a NOP or a move, let's again use the topmost 4 bits to indicate which exact of these basic instructions it is. So let's assign a 2 to the relative jump and a 3 to the absolute jump. We have a whole bunch of instructions that have the lower 4 bits set to a 0, and all of these use the upper 4 bits to encode which exact instruction they are. Even more so, since the jump instructions don't actually use a destination operand, we can set these lower 4 bits here to a 0, which is indicated here. Later on, when we add conditional jumps, we can use these 4 bits here to indicate the jump condition. Next up, we have a whole bunch of arithmetic instructions down here. Let's maybe start with the unary operations. They might be a bit easier. So let's start with not and negation. These operations read and write the RD operand, so I think we just want to indicate this with an RD. But now on top of just interacting with RD and not doing anything with RS, we also want to indicate that these instructions write the flags. They don't read the flags, but they do write the flags. So let's indicate that with a flags exclamation mark. Now let's think about how we can encode this instruction. We've used a 0 in the lowest 4 bits to indicate basic instructions like knobs, moves, and branches. So let me actually take note of this. And since we have quite a few ALU operations, I think it would make sense to assign them a completely different number. Let's say ALU Ops have a 1 in the lower 4 bits. So let's do that for our two instructions. And we can use the same pattern that we used up here for the basic instruction. We can use the uppermost 4 bits to indicate which exact instruction that it actually is. And since the unary operations in the ALU only have an RD operand but no RS operand, these 4 bits in the instruction are not used as an RS operand. They're available for us to encode which instruction that we're executing. So what we can do for unary ALU operations is we can assign them all the exact same value in the uppermost 4 bits as well, and then use the bits where the RS operand would usually be to indicate which exact unary operation that we're doing. So basically, if we see an ALU operation, a 1 in the lowest 4 bits, we can take a look at the topmost 4 bits. If it's a 0, it's going to be a unary operation, and if it's non-zero, it's going to be a binary operation or any of the other ALU ops. Let's continue with the unary operations. We also have all these shifts available and the flag swap. Now, all of these operations are going to read and write the RD operand, but not all of these interact with the flags the same way. So shift left logical just writes the flags, but shift left with carry reads and writes the flags. The other shifts work in a similar way. And then finally the flag swap operation, we're reading and writing the flags. And then let's just keep counting up in bits 8 to 11 to encode these different instructions. Let's encode the binary ALU operations. So most of these instructions just read and write the RD operand and read the RS operand, which is pretty neat. The only exception is compare and test. These two instructions only read the RD operand, but they don't write any result back. So let me indicate that with an RD question mark. And then almost all of these instructions just write the flags, with the exception of add with carry and subtract with carry. Both of those also read the flags. Since these are ALU operations, we'll set the lowest 4 bits to a 1, just as with the unary ones. And then we'll use bits 12 through 15 to indicate which exact ALU operation this is. And we're going to start at 1 because 0 we use to indicate unary operations. And then last but not least, we have the conditional move operation. This one is a bit special because it also has this condition code that it needs to encode. So this looks almost like a load immediate instruction in terms of how expensive it is to encode. So I think it would make sense to actually move this up to the move and the load immediate instructions among the basic instructions. Now, the conditional move reads the flags, but it doesn't write the flags. And since it's almost like an immediate instruction in terms of how many bits it needs for encoding, let's just assign it a fresh new value in the lower 4 bits. Pretty sweet. That's all the existing instructions re-encoded with a bit more of a systematic scheme. But now, since we have this instruction decoder, I think we can be a bit more fancy. For example, this conditional move instruction here takes the value in RS and moves it into RD if a certain condition is set. But we don't necessarily need to read RS as a register. We could also just interpret the bits where the RS operand is as a 4-bit immediate and load that immediate value conditionally into RD. And I think that's all we need. We assign a new number for the lowest 4 bits, and instead of having an RS operand, it has a 4-bit immediate operand. But besides that, this operation will probably work exactly like a conditional move. This was not possible before when we hardwired connections to the instruction bits, but now since we're doing proper instruction decoding, we can have fancy instructions like this at pretty much no cost. Now, back in the early days of the ALU, when we created the first add instruction, we also had an immediate add instruction, and this we had to then remove because we added more functionality to the ALU and we had a clash of the instruction bits there. But now that we have a proper instruction decoder, we can add these immediate instructions back in. Now, it would be useful to have immediate versions of almost all of these ALU operations here, because it would be pretty common to add a constant to a register, or AND or XOR a register with a constant, or compare a register against a constant value. But as we've seen, instructions that accept an 8-bit immediate are actually pretty expensive in terms of how much instruction encoding space that they take up. So I think it makes sense to not create 8-bit immediate versions of all of these instructions, only of the most important ones, and use 4-bit immediate versions for all the others, which are much cheaper because the immediate fits into the same bits as the RS operand. So for example, I think it would be useful to have an add instruction with a full 8-bit immediate. And I'm going to pick the value 12 for the lowest 4 bits of the instruction to indicate that this is an add with immediate. I think we also want to have an 8-bit immediate flavor of the AND the OR operation, because this will make bit manipulation a lot easier. And finally, I think it would also make sense to have an 8-bit immediate version of the test instruction. This might seem a bit odd initially, but I'm pretty sure we'll have cases where we read an 8-bit value from somewhere, for example from an LCD or some other peripheral, and we want to check whether a certain bit is set. And it would be pretty nice if we could do such a bit testing across all 8 bits with an immediate. So this creates 4 8-bit immediate operations right at the end of the encoding space, and slots 12, 13, 14, and 15 for the lowest 4 bits. But I think we can create a few more immediate instructions, but maybe just with 4-bit immediates. For example, if we have a 16, 24, 32-bit value that we're trying to count up, or we're adding an 8-bit value to a 16-bit value, we would use an add on the lower 8 bits, and then we would just want to increment the upper 8 bits in case there was a carry generated. And having an add with carry and immediate would be pretty useful because we could just add the immediate 0 with the carry to accomplish this. And since the immediate here fits into the exact same bits as the RS operand, this instruction looks pretty much like all the others. It's just that we're interpreting the RS bits slightly differently. While we're at it, we might as well have an XOR with immediate in case we want to flip the lower bits in a register. And finally, for loops and some other bits and pieces, it might be useful to have an immediate flavor of the compare operation. We'll just use a 4-bit immediate again, so we can only compare against very small numbers, but that might be enough for quite a few use cases. Okay, that looks pretty good. So we have a whole bunch of immediate flavors of the ALU instructions, which is going to be pretty useful in practice, I think. Let me also make sure that we don't forget about the halt instruction. Since we haven't changed the encoding of the jump relative with immediate, this will just stay the same. This is going to be a pretty good starting point for an instruction encoding. Let's switch back to the decoder and actually write up the decoding scheme for these instructions. The way we have organized the instructions, we have used the lowest 4 bits of the instruction as kind of the main initial indicator as to what the instruction is supposed to do. So let's call the value in this bit range function 0. And if this function 0 value is a 0, this is one of the basic instructions. So let's try to decode those. For example, if all instruction bits are 0, this is a NOP, and we can just return the default values for the decoded instruction, because all we want to do is step to the next instruction without changing anything in the register or flags. Then we've used bits 12 through 15 to indicate what kind of instruction among the basic instructions this is. For example, the move here has the value 1, and a bit further down, the jump relative with register and jump absolute with register have values 2 and 3. So let's call the value in this bit range 12 to 15 the function 1 value. And so if we're decoding a basic instruction where func0 is 0, we can check this func1 field, the topmost 4 bits, to figure out what instruction we're supposed to execute. If func1 is the value 1, this is a move. And since we've already indicated what the exact RD and RS mode is in the instructions at architecture file, we can more or less just translate this into our decode function. So a move just writes the RD operand, it reads an 8-bit register value as the RS operand, and since this is a move, we want to send this to the move functional unit. Next up, we have 2 jump instructions. So if we see the value 2 in bits 12 to 15, we're doing a relative jump. And in this case, we don't want to do anything with the RD operand. We just want to read an 8-bit value from the registers for RS. And the program counter mode we want to set to relative jump. And let's not forget about bits 4 to 7, which we have explicitly set to the value 0 here, because we might want to use the same encoding where bits 4 to 7 are non-zero to indicate a conditional jump. So let me call this bit range in instruction function 2. And I think in the future we might want to rename these jump instructions to something a bit shorter. So this instruction I think we want to call JRO, jump with register offset. Now let me do the same thing for the absolute jump, which has function 1 set to the value 3. And in this case we are reading a 16-bit value from the register file as an RS operand. Let's quickly figure out what we should do if we don't recognize this instruction. So basically when we arrive down here at the end of the decode function and none of the other return statements have triggered. Ideally in this case we would generate some kind of exception in the CPU here, but that's way in the future. I think for now, let's just create the default decoding for the instruction, but let's set the PC mode to the reserved bits. These aren't really used and not hooked up fully, but I think the program counter will just jump back to the value 0. The effect of this would be that whenever we see an illegal instruction that we do not understand, we would just reset the CPU, which is a good initial behavior, I think. So this will make it nicely obvious when we have illegal instructions in the program. Now let's decode a few first immediate instructions. For example, we have this jump relative with immediate here. This instruction has the lowest 4 bits, the function 0 field, set to the value 9. In this case, we want to set the RS mode to 8-bit immediate, and we want to set the program counter mode to a relative jump, and everything else we leave at the default. The relative jump also has bits 4 through 7 set to 0, and we want to reserve this to contain a condition in the future. So let's also check that func2, which is the range 4 to 7, is the value 0. Then let's add the load immediate, which has the function 0 field set to 8. In this case, we want to write the RD register and use an 8-bit immediate value for the RS mode and throw this at the move functional unit. That looks pretty good. Next up, I think it would be good to start tackling the ALU operations. Let's start with the Unary Ops. All the ALU operations have the lower 4 bits, the function 0 field, set to the value 1. And then Unary operations have the uppermost 4 bits, the function 1 field, set to 0. And now for the unary operations, we've used bits 8 through 11 to indicate which exact instruction this is. So let me call this range of the instruction the function 3 field. And we can now check this function 3 field to distinguish between the unary operations. For example, a not has the value 0 in func3. And since we're going to have quite a few ALU operations, let me create a helper function that creates the decoding for unary operations, because they look almost the same. And we also want to create a new enum that contains the different ALU operation that the ALU functional unit supports. Let me go steal the ALU operations from the ALU decoder. And then let's define that function that creates the decoding for Unary ALU Ops. This will accept the ALU operation we want to execute, and then optionally also how we interact with the flags, because not all unary operations have the same interaction with the flags, but the majority of them will write the flags, so by default we'll just set the flags to write only. And the unary operations are pretty straightforward. We're going to read and write the RD operand. We're just going to use the provided flags mode. We're going to select the ALU as the functional unit, and we can just pass through the ALU opcode. Alright, I think this will do the trick. Let's do this for the remaining unary operations. The shift left with carry is a bit special because it also reads the flags, so we have to specify a different flag mode here. And that's all the unary ALU operations handled. While we're on a roll, let's do the same thing for the binary operations. The binary ops use the function1 field to indicate which instruction should be executed. So we use this to decide what instruction we're looking at. Again, let me create an ALU binary helper function that just creates the decoded version of a binary ALU op. This will again accept the ALU operation we want to execute. And then by default, we'll set the flags to write only. We'll set the RD operand to read and write mode. And we'll set the RS operand to just read 8 bits from a register. Again, we'll select the ALU as the functional unit, and we'll just forward the ALU opcode. So let's do this for the remaining binary operations. The add with carry requires a special flags mode because it additionally also reads the flags. And or an XOR are pretty straightforward. And then somewhat special are the compare and test instruction, because these actually don't write back to the RD operand. They just read the RD and the RS operand, perform a subtraction or an AND operation, and then update the flags accordingly. So the compare operation, for example, actually uses a subtraction in the ALU to perform the comparison and update the flags. But the RD mode is set to read only, such that we don't accidentally write the result back into the register. And the test works in a similar way, but it uses an AND operation in the ALU. And then we also have a few instructions that take a 4-bit immediate operand. And these are going to be a bit special to encode. So let's start with the add with carry, which is function 1 set to the value 10. This is going to work the same way as the regular add with carry, but the RS mode is going to be set to the immediate 4 mode. Then we also have an XOR with immediate. And finally a compare with immediate, which works the same way as the regular compare, but we're picking the 4-bit immediate mode for the RS operand. We're almost done with ALU operations, but we have 4 more immediate versions of the ALU instructions, and these with 8 bits. And again, since these are 8-bit immediate operations, they use the lowest 4 bits, the function 0 field, to indicate which operation it is. And these all work the same way as the register version of the instruction, but they have the RS operand mode set to 8-bit immediate. So I think that's all the instructions decoded properly. And having written the instructions up in an instruction set architecture document like this, with precise indications about which registers are read, written, and whether the flags are read and written, makes this a pretty straightforward process. And it looks pretty mechanical, so there's a high chance that in the future we should be able to just read this instruction set architecture document with a script and generate the decoder automatically. But we'll figure that out a bit down the road. The only thing missing from the decoder are the conditional move and conditional load with immediate instruction. Let's deal with the conditional move first. This has the lowest 4 bits, the function 0 field, set to the value 2. In this case, we're interpreting bits 12 through 15, the function 1 field, as the condition code. And the conditional move is a regular binary ALU operation, but we're merging the conditional move opcode, which is just the topmost bit set, with the condition code, which then sets the lower 4 bits of the ALU operation. And since we're just reading the flags to decide whether to do the move or not, but not writing them back, we set the flags mode to read only. Then let's do the same thing for the conditional load immediate. This instruction is identical to a conditional move, but we're setting the RS operand mode to 4-bit immediate instead of a regular register read. That is pretty cool. So since we have a proper instruction decoder now, which is essentially an arbitrary Boolean function from 16 bits to another 16 bits, we can be a lot more clever about what kinds of instructions we want to have and how they set the different control signals of the CPU. And we'll extend this a lot in the future with a lot more fancy instructions. Let's run this again. So it looks like this still works, and it updates the ROM data. And it's hard to tell from just looking at the data like this, but it looks like we have a slightly different pattern in here than we had before. That is very promising. So now that we have updated our instruction set architecture, I think it would be nice if we could also write programs using these new instructions. So it's time to go update our assembler. We've had this assembler test program here. I think it would be nice if we cleaned this up a little bit and added one example for each instruction in the processor, just as a kind of smoke test to see if everything works. Let's run the assembler on this. This is all still working, but it's also using the old encoding for these instructions. So let's go into the assembler itself and let's update these opcodes. The encoding for the NOP hasn't changed, so we can leave that as it is. The load immediate also hasn't changed, it just uses an 8 in the lower 4 bits, but let me use a decimal notation. The move sees the first change. The lowest 4 bits we've set to a 0, and the topmost 4 bits we've set to a 1. And the rest of the encoding stays the same. Our jumps have also changed. Our jump absolute with register instruction has a 0 in the lower 4 bits, and it has a 0 in the function 2 field, and a 3 in the topmost 4 bits in the function 1 field. Then we have our jump relative with immediate, which still has a 9 in the lower 4 bits, but also let me separate out the function 2 field here. And then the jump relative with register uses a 0 in the lowest 4 bits, a 2 in the topmost 4 bits, and a 0 in the function 2 field. Let me run the assembler again. And this now produces the new encodings for these instructions, which is pretty neat. Let me add a conditional move and a conditional load immediate to the test program. Now when I run the assembler, this breaks because we don't know what a conditional load immediate is. So let me add that. Then for the encoding, the conditional move instruction has also changed. We are now setting the lowest 4 bits, the function 0 field, to the value 2. And we don't have to set this bit number 11. And the conditional load immediate is going to work pretty much the same. The only difference being that the lowest 4 bits are set to the value 3, and we're encoding a signed 4-bit immediate for the first time. So let's create a new encode function for this. We already have one for signed 8-bit immediates, so this should be pretty straightforward. We have a very limited value range of -8 to 8, and this immediate goes into the bits 8, 9, 10, and 11. Let me run the assembler again, which seems to work. We see a whole bunch of conditional move instructions up here, with the lowest 4 bits set to a 2, indicating a conditional move, and the topmost 4 bits set to the condition code, and then a conditional load immediate with the lowest 4 bits set to a 3 to indicate the conditional load with immediate, and the topmost 4 bits set to a condition code. And you can see the immediate itself gets encoded into these 4 bits here, a 4 for a +4, and a C for a -4, which is just the 2's complement representation of -4. Let's also go and test the branch instructions. Let's test both negative and positive jump offsets. I've also off-screen swapped the order of register pairs around. This used to be R0, R1 initially, but I think it's much more easy to understand what's happening if it's R1, R0, because the value in R0 is going to be the lower bits, which is going to be on the right if you wrote the number out, and R1 is the higher bits, which is going to be on the left of the number. This should still work, and it does work. We get the jump instructions as expected. Jump relative with immediate hasn't really changed in the encoding, but here you can see the new jump relative with register and jump absolute with register, which have a 0 in the lower 4 bits for function 0, and a 2 and a 3 for the function 1 field. Then let's test the unary arithmetic operations. And we also need to update the encoding for these in the assembler. Then let me run the assembler. And that seems to work. We get a whole bunch of unary ALU operations. All have the lower 4 bits set to a 1 to indicate an ALU operation, the topmost 4 bits set to a 0 to indicate a unary operation, and then they use the next 4 bits up here, where usually we have the RS operand, which isn't used here, to indicate which exact unary operation this is. Pretty sweet. Let's do the same thing for the binary arithmetic. So these are the basic instructions we've already had in the processor, but now we have a few additional immediate flavors of these operations that we might want to mix in here. This won't work with the assembler because it contains new instructions. So let me go add the missing instructions and update the encodings. And now when I run the assembler, we get all the old and new ALU operations encoded properly, including the new immediate operations we have with both 8-bit and 4-bit immediates. That is pretty good. With this add immediate here, for example, you can see that the lower 4 bits are set to C, which is the number 12, which indicates an immediate add. And the -42 here gets encoded into the upper 8 bits of the instruction. And then compare this to, for example, an XOR with immediate, which has the lower 4 bits set to a 1 to indicate an ALU operation, the topmost 4 bits set to B, 11 to indicate an XOR operation, and the 3 immediate is packed into the bits where usually the RS operand would be. And then same for -3, we just have the 2's complement representation of this in the same bits. So that's the assembler updated to match the newest version of our instruction set architecture. And I think it's now time to actually go and write a new program using these instructions. In the past few episodes, we've been running this conditional move testing program, and at the end computed the largest 16-bit Fibonacci number. I think it would be cool to have this Fibonacci number computation pull out into its own test program. To get started, let me clear the registers to 0, just as we're used to doing. And then let's also clear the flags register. This will copy any garbage from the flags into the R0 register, so we'll have to set R0 back to 0. And then let's use the first 6 registers in pairs as variables for the Fibonacci sequence computation. This is pretty straightforward since the registers are already 0, so all we have to do is store a 1 in register R2 to have the first 2 Fibonacci numbers, 0 and 1, in registers R0, R1 and registers R2, R3. And then let's enter the loop where we actually compute the Fibonacci sequence. First up, we want to move the variable A into the variable C. Then we want to move the variable B into A. And then we can compute the next Fibonacci number by adding C to B. And since we're dealing with 16-bit numbers, we first do an add on the lower 8 bits and then an add with carry on the upper 8 bits. And then after this last add with carry, if we've gone beyond 16 bits and we produce an overflow, the carry flag will be set. And we can now use this to create a conditional jump. Before we enter the loop, we can load a register, for example R6, with a relative jump offset that allows us to keep iterating in the loop. And then we can use the new conditional load immediate instruction to overwrite this jump offset with the value 2 to break out of the loop in case the carry flag is set. And then afterwards, we just use the value in R6 as a relative jump offset. And now from this jump relative with register instruction, we have 7 instructions, that is 14 bytes to the beginning of the loop. So we can load the R6 register with the value -14. This will cause this jump relative with register to jump back to the beginning of the loop up here, unless this conditional load immediate has happened, in which case the relative jump offset in R6 will be set to the value 2, which is just going to jump to the next instruction, which is effectively whatever follows after the exit label here. In an earlier version of this program, we had to use a conditional move here, which also means that the value 2 we're loading into R6 had to be stored in a temporary register somewhere. And this meant that even for this simple program, we were already getting a little bit tight on the available registers. And once we have conditional jumps, this is going to be even easier because we can do away with the register R6 completely and just use a jump relative with immediate here to jump back to the loop, but only under the condition that the carry flag is not set in this case. And then down here, once we break out of the loop, I think we want to clear all the registers back to 0 except for the result, which we want to stay there. And once the registers are cleared, we'll just halt the processors. And at that point, the register pair R1, R0 should contain the value 46,368, which is the largest Fibonacci number that fits into 16 bits, a number which we've seen countless times in the previous episodes. Let's see if we can assemble this. This looks pretty good. Let me turn this into a binary. And then all that's left to do is to write the new decoder ROM data into the decoder ROM chips and this new program into the program memory. Let me power this up and let's give it a try. So we have an all new program here in the program memory and a completely new instruction decoding scheme programmed into the instruction decoder. Let's step through a few instructions and see what happens. First, let me step it out of reset. And then we're going to clear the register file as per usual. We're doing this with a load immediate instruction. We're loading the immediate 0 into register R0. And this happens to be the exact same encoding as we had before, just by coincidence. But now the instruction decoder is a bit more careful about how it decodes this instruction. As you can see, the lowest bit is set, which means we're not reading the RD operand, which is correct because we're just writing an immediate value into register, so we don't need to read what is already in the register. The second bit is 0, which indicates that we are writing the RD register. And then bits 2 and 3 indicate the RS operand mode, and it's set to the value 2, which is the 8-bit immediate mode, which is also correct because we were loading an 8-bit immediate value and storing it into a register. And then bit number 4 is a 1, which indicates that we're not reading the flags, which is correct for the load immediate op. And bit number 5 is also a 1, which indicates that we're also not writing the flags, which is also correct for a load immediate operation. And if you recall how this worked before, the CPU was always reading the RD operand. So the first read data port of the register file would always carry the value of the register we're also writing into. But now, since we're more careful about indicating which registers we do read and write, you can see that the CPU no longer reads any value on the RD1 port. And similarly, since the RS mode is set to immediate, we're also not reading anything on the RD2 and the RD3 port. So quite correctly, in this load immediate operation, which just writes something into a register, none of the registers is actually being read. And this is going to be very important in the future if the CPU wants to detect if there are any collisions or hazards between operations in the CPU, it has to know very precisely which registers are being read and written, because it needs to check if any of the read registers is not ready yet, hasn't had its result written into it, and it has to stall execution of an instruction if that is the case. And so we don't want to gratuitously indicate that we're reading registers which we're actually not reading, because those might cause the CPU to stall the instruction because it thinks we're actually reading something from the register file that isn't ready yet, even though the instruction doesn't actually need the value. So this new instruction decoder with the precise read and write bits on the RD operand, the RS operand, and the flags make this possible and allow the CPU to very carefully orchestrate and figure out which registers are actually needed to execute an instruction, and also whether the flags need to be written or read. And on the second ROM of the decoder, you can see that the topmost bits are 0, so we're selecting the move functional unit, which makes the move output enable active, and the immediate output enable is active because we're selecting an immediate mode on the RS operand. And when I hit the clock, the value 0 is going to be written into R0. You can't really tell because the register was already 0, but at least it looked like the control lines were set correctly. Next up, we're doing a move from R0 into R1. You can see our new instruction encoding in action here. The lower 4 bits are 0, which indicates a basic instruction, and then the uppermost 4 bits are set to the value 1, which indicates that this is a move instruction. And then the other 4-bit nibbles of the instruction indicate the source and destination register. And again, the decoder produces pretty precise information of what's going on in the CPU. The lowest bit is set, which means we're not reading the RD operand, which on the register file means no register is selected for reading on the first read port. Bit number 1 is a 0, which means that we're writing the RD register. And as you can see, we're indeed selecting register R1, which is our RD register in this instruction, for writing. Then bits 2 and 3 are 0, which indicates that we're reading an 8-bit value from the register file as the RS operand. And indeed, register R0 is selected for reading on the RD2 port. And currently, we're also selecting it for reading on the RD3 port, because this is how we've wired things up. But in the future, we'll only want to enable the third read data port if the instruction decoder indicates that we're reading a 16-bit value. Because again, the CPU might use this information to detect hazards between the instructions and decide when to stall an instruction. And so we don't want instructions to indicate that they read something on the third read data port if they don't really need that value. And then bits 4 and 5 are both 1, which indicates that we're not reading the flags and we're also not writing the flags. And again, we're selecting functional unit 0, the move unit, and it has no opcode because all it does is move values between the read and the write data bus. And so when I hit the clock, the 0 in register R0 is going to be written into R1, but again, you can't see anything because R1 already contained the value 0. But now things get a bit more interesting. This is still a move instruction. Lowest 4 bits are 0, topmost 4 bits are 1, but this time we're moving from R1 into R2, and R2 is a non-zero value, so we should see this be overwritten. And indeed, when I hit the clock, register R2 is set to the value 0. And then we're going to do this for the remaining registers. And now we're going to do the same thing for the flags register. We're going to clear it to 0. So the next instruction is a flag swap instruction with register R0. We expect the flags value to be copied into register R0 and the 0 value that's currently in the register to be copied into the flags. And again, you can see the new instruction encoding in action. The lowest 4 bits are set to a 1, which indicates an ALU operation. The topmost 4 bits are set to 0, which indicates a unary ALU operation that doesn't need the RS operand. And since we don't need the RS operand, we can use the bits where the RS operand would usually be to indicate what the actual ALU operation is. And the 7 here indicates that this is a flag swap operation. And correspondingly, the decoder sets the 2 lowest bits to 0, which indicates that we're both reading and writing the RD operand, which is R0. Bits 2 and 3 are the RS mode, and this is set to a 4-bit immediate because we're not really using the RS operand, and so we don't want to artificially read something from the register file which might cause stalls in the CPU later. But since we're doing a flag swap operation, the decoder now indicates in bit number 4 and 5 that we're both reading the flags and writing the flags. And indeed, you can see the flags write enable is active, so we're writing into the flags. And since we want to copy the current value of the flags into R0, we're also reading from the flags register. Currently, we're not doing anything with the information about if we're reading the flags or not, but again, later on, when we need to detect if there are any stalls or hazards in the pipeline, it will be interesting to know if an instruction needs the flags, and the flags are currently waiting to be computed because some other instruction is in flight. And since this is a flag swap in the ALU, the second decoder ROM sets the functional unit to 1, which is the ALU, so the ALU gets selected and produces results, and the opcode is set to the FSWAP operation in the ALU. Now it's interesting to note that in the instruction encoding here, we've used the value 7 to indicate that this is a flag swap unary ALU operation, but the actual opcode that is sent to the ALU is the value 12, which is not the same. And beforehand, when we had this simple instruction decoding scheme where we just connected the bits of the instruction with wires to some of the control signals, we had to put the exact ALU opcode, the 12, somewhere in the instruction. But since we now have this Boolean function in between the instruction bits and any of the control signals, we can come up with much denser and more optimized encoding schemes for the instructions, and then figure out what we actually need to send to the different parts of the CPU. So when I hit the clock now, we're going to see the value 1 from the flags appear in register R0, and the 0 that's currently in register R0 appear in the flags register. And that's exactly what happens. The 1 got moved up here into R0, and the 0 got moved down into the flags register. Pretty nice. And now we're doing another move. We're moving the 0 from register R1 into register R0, just to clear it back again. So the register file is cleared, the flags are cleared, so we can now finally start to compute the largest 16-bit Fibonacci number. And we're going to do this by loading the immediate value 1 into register R2. And again, we've seen this before, this is a load immediate, so the instruction decoder indicates that we're not reading the RD operand, but we're writing the RD operand. The RS operand is just an 8-bit immediate value, and we're not interacting with the flags at all. And so when I hit the clock, that 1 gets deposited in register R2. Then we're loading the immediate value -14 into register R6. This is going to be our loop jump offset. And indeed, you can see -14 on the right data bus here of the register file, and register R6 is selected for writing. And again, the CPU is much more precise now. None of the other registers is selected for reading, which is pretty sweet. So that -14 got deposited in register R6, and now we're entering the loop where we're computing the Fibonacci series. First, we're moving the value in R0, R1 into R4, R5. Then we're moving the value in R2, R3 into R0, R1. And now we're going to add the value in R4 to the value in R2. So this is an add instruction in our new encoding. You can see the lower 4 bits being set to a 1, indicating an ALU operation. Then the uppermost 4 bits are set to a 1, which indicates that this is an add operation. And then the other 4-bit packets here indicate the source and destination registers. And again, the decoder is pretty precise. It indicates that we're both reading and writing the RD operand. Then the next 2 bits are 0, which indicates that for the RS operand, we're just reading an 8-bit value from the register file. Then bit number 4 is set, which indicates that we're not reading the flags, which is correct for the regular add operation. But bit number 5 is 0, which indicates that we're writing the flags, which is accurate for the add operation. We're not using the carry flag for this add operation, but the add operation will set the carry flag according to its result. And so when I hit the clock, we're going to see this 0 being added to this 1 here, which is just going to produce the 1 that is already there. And immediately after this, we have an add with carry, which again is indicated by a 1 in the lowest 4 bits to indicate an ALU operation, and then a 2 in the topmost 4 bits, which indicates an add with carry. And now the decoder output has changed slightly. We're still writing the RD operand, and the RS operand is set to just read 8 bits from the register file. But now we're indeed reading the flags, indicated by bit number 4 being cleared, and also writing the flags as before. It's indicated by bit number 5 being cleared. And this is because this is an add with carry operation, and this operation does read the current state of the carry flag and incorporate it into the addition result compared to the regular add we've executed before. So now the CPU knows pretty precisely that for the add with carry operation, it does have to provide the current state of the flags register to the ALU, whereas for the regular add operation, the ALU doesn't care about the flags. And so later on, when we do out-of-order execution of instructions, if the CPU is currently computing an instruction somewhere in parallel that produces flags, we can execute an add operation because it doesn't need the flags. But if we were to execute an add with carry operation, we do need the flags, and so the CPU would have to stall and wait for the other instruction that's currently computing the flags to finish, such that the add with carry operation can then pick the flags up that were produced and use it for its own computation. So when I hit the clock, we're going to see the 0 be added to the 0 up here, and since the carry is also 0, the result is just going to be 0, so very boring. Pretty sweet, that worked. And now we have a completely new instruction, the conditional load immediate on carry, which is quite a mouthful. We can have this operation because we now have an instruction decoder which can be pretty precise about how it sets the flags. In this new encoding, the lower 4 bits being set to 3 indicates that this is a conditional load immediate, and the topmost 4 bits indicate the condition under which we want to do the load. And the 2 here indicates that we only want to load if the carry is set. And the lowest 2 bits of the decoder indicate that we're reading and writing the RD operand. And this is actually correct since we're doing a conditional load immediate. The ALU must have the option of producing the current value that is already in the register as its result, such that we're actually not changing the value. So before, when we did a regular load immediate, the decoder indicated that we're not even reading the RD operand because we're just plainly overriding the value anyway. But now for the conditional load immediate, we have to additionally read this value. So that's pretty cool. Then we have the RS mode in bit number 2 and 3 set to the value 3, which is the 4-bit immediate mode. And this is the first time we're using this mode in any instruction. And as you can see, this commands the move and immediate buffer down here to enable the immediate mode, but also to set the immediate to 4-bit mode, which takes the lower 4 bits of the immediate and sign extends it to an 8-bit value. So we're using bits 8, 9, 10, and 11, which is where usually the RS operand would be in the instruction, and we're treating it as the lower 4 bits of an immediate value and sign extend that. And correspondingly, you can see the same value, the value 2 here, appear on the RD2 port, extended with zeros, because the topmost bit of the lower 4 bits is 0 as well. So this is pretty convenient because we now have much more flexibility in how we decode instructions and assign the control signals. We can pretty easily create such a load immediate instruction that is similar to the conditional move, where we just interpret a part of the instruction as an immediate instead of as an register operand, and then send that to the ALU. Bit 4 is low, which indicates that we're reading the flags, which is correct. This is a conditional move, so this needs access to the flags. And bit 5 is high, which indicates that we're not writing the flags, which is also true. This is a conditional load immediate, and the same as a conditional move, we want to read the flags, but we don't want to actually write anything back to the flags. We want to keep them undisturbed. And then on the second decoder ROM, you can see that we're selecting functional unit 1 to execute the instruction, which is the ALU, and the opcode is a conditional move on carry. So this instruction behaves exactly like a conditional move. The only difference is that we're not feeding a register value into the ALU, but an immediate value. But this is actually done outside of the ALU as part of this flags move and immediate buffer PCB down here. And I think this is going to be a pretty useful scheme later on when we have more complicated instruction issuing and maybe a reorder buffer. At the time when we decode the instruction, we can already decide if we ever need to look up a register, or if we're using an immediate value anyway, and we already have a value available that we can send into the reorder buffer. So when I hit the clock, because we're doing a conditional move and there's no condition match up here, we should see the register down here not update at all. And that is exactly what happens. Very neat. Next up, we're doing a jump relative with register. The lower 4 bits of the instruction being 0 indicates that this is one of the basic instructions, and the value 2 in the topmost 4 bits indicates that this is a relative jump with register. The decoder tells us that we're not reading the RD operand because the lowest bit is set. We're not writing the RD operand because bit number 1 is set. But we are reading the RS operand as an 8-bit value because the next 2 bits are a 0. And we're not reading and not writing the flags as indicated by the next 2 bits. And this is correct. This instruction does not use the RD operand at all. It just uses the RS operand to read a register and use it as a jump offset. And because this is a control flow, a jump instruction, the topmost 2 bits of the first decoder are non-zero. In fact, they're set to the value 1, which indicates that we're doing a relative jump here in the program counter. And correspondingly, you can see that 1 appear here as the program counter mode selection. The second decoder ROM selects functional unit 0, which is the move unit. But since we're not writing to the RD operand, this isn't actually doing anything. And since we're using the topmost bits of the first decoder ROM to control the program counter mode, this second part here, the second decoder ROM, is actually completely ignored. And I think this is an inefficiency. In the future, what we'll want to do is we probably want to move these 2 bits that we have up here into a dedicated functional unit that corresponds to the program counter. So we'll have another index up here correspond to the program counter. And whenever the program counter is not selected as a functional unit, it's just going to do a regular stepping to the next instruction. But when we select the program counter as a functional unit, we can then control the mode that the program counter steps in with a few of the bits here in the opcode. And this will then allow us to have 2 more bits up here from the first decoder ROM to control other things in the CPU. Because control flow instructions are the only ones where we actually want to influence how the program counter behaves. So it makes sense to not encode a program counter mode for every single instruction, but to kind of tuck that away behind an actual functional unit. And this will also then allow us to have conditional jumps much more easily. So we're now at program address hex 24, and when I hit the clock, we should see this jump back by 14 bytes as indicated by the register we're using as a jump offset, which should make us land on hex 16. Which works, and we're now back to the move instructions, moving stuff around in the register file, and then doing the addition for the Fibonacci sequence. So it looks like this is working. Let's be bold and just hit run, because there's going to be around 20-ish iterations that are needed to actually compute the largest Fibonacci number in 16 bits, and I don't want to step through that manually. So when I hit run, we should see the first 2 registers as a pair count through the Fibonacci numbers up to the largest one, and the program should then stop. Pretty nice. We broke out of the loop, which means that the conditional load immediate is actually working, and as soon as the addition started to overflow, we changed the jump offset of the relative jump to break out of the loop, and then we cleared all of the registers except for the result registers. And indeed, this is still the value 46,368, the largest 16-bit Fibonacci number. This is pretty exciting. We now have a fully fledged instruction decoder, and we were able to come up with a completely new encoding for the instructions that we have and add quite a few more instructions. And we haven't really used all of them yet, so this will come in the future. But we're able to write programs in this new instruction encoding and execute them and still compute the largest Fibonacci number, which is about the fanciest thing that we've been doing on this CPU. But this now opens the door for a lot more complicated and fancy instructions. One of the things I would like to add is a conditional jump instruction, which similar to the conditional move, which inspects the flags and then decides what to do, if it should do a move or not. I would like to have a similar jump instruction where it actually consults the flags and checks for a matching condition, and only then actually switch the program counter into jump mode. And if the flags don't match a certain condition, just continue with regular stepping, so basically just stepping to the next instruction. And that will allow us to have much more compact conditional jumps, which allows us to do if conditions and for loops very efficiently in a program. This decoder will also allow us to add more functional units. For example, I think it would be nice to have a control and status register component for the CPU, which is usually just a grab bag of registers and other things your CPU might want to read or write that aren't really commonly modified and part of the regular instruction flow. So one of the things we could use that for is attach an LCD to the CPU, such that you have something to write a little bit of text output to. And having a dedicated control and status register unit will allow us to talk to such an LCD just as if it were another register that we can access in the CPU. And this will then also allow us to attach other things to those status registers, such as a cycle counter, which will be very interesting to actually measure how long certain programs take to execute. And I'm pretty sure we can come up with other things that we might want to put there. And then glaringly missing right now from the CPU is any kind of memory except for 7 bytes worth of registers, which isn't a lot. So it would be nice to at some point attach a little bit of RAM to this CPU and get a very simple load store unit, which is going to be another functional unit that we attach to the decoder to actually interact with that RAM. And I have a feeling that once we have that, once we have an LCD in the RAM, we're going to start running into an issue where we have instructions in the CPU that take multiple cycles or that might contend for memory accesses. That will be a very good excuse to go in and figure out how we can stall execution of the pipeline of the CPU. Because there are 2 reasons for which the CPU might not be able to do any work. It could be starved of instructions. For example, when the load store unit wants to read from the program ROM and the CPU wants to fetch the next instruction from program ROM, these 2 accesses are going to contend, and the CPU will effectively have to give way to the load store unit to deal with its load for it to be able to make progress. So there's going to be a cycle where the CPU is actually starved in a sense where there's no instruction flowing into the CPU. On top of that, the CPU might be trying to send an instruction to a functional unit that isn't ready to accept new instructions yet. I'm pretty sure that the LCD we're going to attach to the CPU has pretty strict and slow timing requirements, so the CPU wouldn't be able to run at full speed and still interact with the LCD. So there's probably going to be a scheme where we write to the LCD, but the write to the LCD takes a few cycles in the background to meet all the timing requirements of that slow peripheral. And if the CPU tries to do 2 writes to the LCD back to back, the second write will have to wait a bit because the LCD will not be ready to accept new instructions immediately. So this will be a situation where a functional unit will have to be able to provide back pressure into the CPU pipeline and basically stall the CPU from the back and make it wait until it's ready to accept new instructions. And once we have a scheme where we can stall the CPU from the back or from the front, we'll be able to do more fancy things in terms of parallel execution. If we have a few units that take multiple cycles to execute, for example, we could try to build up a hardware multiplier that takes a few cycles. We could still try to have the CPU execute unrelated instructions immediately after and only stop and stall when we're trying to access a result from an instruction that is still in flight. I think that's going to be our first venture into the realm of out-of-order execution. And once we have such a scheme where things can run in parallel and also write back to the register out of order, the question will come up how we can also issue and start instructions out of order, such that we can skip instructions that are currently blocked and execute instructions further down in the program already if all their operands are present. But that's going to take a little bit of remodeling here, and we first need to be able to stall the pipeline, and it will probably also be good to have a little bit of memory and some display just to be able to run some programs and have something to look at. And as we've seen when we updated the assembler just before, it's really due for a little bit of refactoring and cleanup. And since we now have a proper decoding scheme here, I think we can also look into a bit more of a systematic way to encode instructions on the software side and how we can describe instructions once and then maybe derive things like an assembler or maybe also an ISA manual from that in a systematic fashion. So there's a ton of things to do. I can't wait to extend the CPU further, get a few more peripherals in here, get some memory in here, and make it actually do some more interesting things, and then start to look into the really juicy things on how to make this out of order, how to make this stall properly, etc. Can't wait to make that happen. Like and subscribe if you want to see more of this, and see you next time.